All right, hello. My name is Alex Friedland, and today I'm going to be telling you about my research. So graphene, as many of you know, is a 2D lattice, hexagonal lattice of carbon atoms. I'm showing the band structure here, and it's unique and it's got a lot of attention recently because of course, these Dirac points or valleys, which exist in the first Brillouin zone. There are 6 of them, but only 2 of them are unique, so we label them K and K prime. And the concept of trying to use this valley degree of freedom as a binary 2-state system, right, is the field of Valley-Tronics. And so if you're interested in learning more about that, I refer you to this paper in the bottom left. But the idea is, well, first thing we need to do is induce a Valley-Polarization, which means, for example, exciting electrons in just the K valley while leaving the K prime valley alone. Because if we could do that, then we could create a current of only K electrons, and perhaps that represents a 1 in our binary system. So let's take a moment and zoom in on one of these Dirac points to learn a little bit more. So here I've plotted a cross-section of one of the dispersions around the Dirac point. And on the right, I have my schematic diagram of monolayer graphene. In monolayer graphene, the K and K prime values are indistinguishable due to the presence of inversion symmetry. We can go to a bilayer of graphene, which is just 2 pieces of graphene stacked on top of each other, and the bands go from being linear to parabolic, the low energy bands anyways. We still have inversion symmetry, but we can break the inversion symmetry by putting a potential difference across the 2 layers. And if we do that, we open up a band gap. Not only that this band gap is then tunable by controlling the strength of that bias. So as I crank up the bias, the band structure evolves. This is all well-known stuff. And for example, I refer you to this paper here for a review of the electronic properties of graphene. It's also well known that in graphene, with broken inversion symmetry, one can then excite electrons in a particular valley by using circularly polarized light. So for example, with right-hand circularly polarized light, I can couple predominantly to the K valley and ignore the K prime valley. So therefore, it becomes possible to induce a valley polarization in bias bilayer graphene using circularly polarized light. And in this talk, what I hope to answer for you is, well, what are the conditions that lead to a strong valley polarization? How strong actually can we get? How strong of a valley polarization can we achieve? And then finally, what are the optimal operating parameters for the system? So let's get into the math a little bit. This is the math slide, I warn you. Our Hamiltonian is shown up in the top left. H naught is the Hamiltonian of unperturbed bias bilayer graphene, eigenstates of which are block eigenstates, and the energy eigenvalues are the dispersions, which I showed you on the previous slides. We're going to introduce a perturbation, which will take to be this term here in our Hamiltonian. So E here is the electric charge, R is the position operator, and E is the electric field, which we'll take to be a classical field. In particular, a right-hand circularly polarized field, which has this envelope function out front, which we'll take to be a Gaussian, and it's centered at a frequency omega. Notice we're working in polar coordinates here. Next, one can show that the matrix elements of the position operator with respect to the energy eigenstates of the unperturbed Hamiltonian take the form here, where A and B are real and positive functions of the bias, A, little a, and the wave vector K. And crucially, notice that the form of this function looks different depending on whether we're in the K or K prime valley. Now, the graphene field interaction itself is proportional to the dot product of the position operator and the electric field. And one can easily show that the resonant term, the dominant term of that interaction, is proportional to this thing here. Again, A and B are real and positive, so when we're at the K point, we get a constructive interference, so to speak, of the A and B functions, while at the K prime point, we get a destructive interference. And so if we're trying to achieve a strong valley polarization, we desire A and B to actually be equal, because if A is equal to B, then at the K prime point, we get a perfect cancellation of these two functions and a strong valley polarization. So is that even possible? What are these functions A and B? Well, that's what I'll try to answer on the next slide. So here, I've plotted two things. So let me explain what's going on. Along the x-axis, I've plotted the wave vector, k. You can think of this as the top right-hand quadrant of those energy band plots I showed you a bit earlier. On the leftmost y-axis here, I have the ratio of the functions a and b at a particular bias, a in this case, and that's corresponding to this dashed line here. And then on the rightmost axis, I'm plotting just the energy dispersion, and that corresponds to the solid curve. Now remember, we desire A equal to B, or another way to say that is we desire A over B is equal to 1. And so right away, we see that A over B is equal to 1 exactly at k equals 0, i.e. right at the Dirac point, which is, you might expect, as it's a high symmetry point. But the AB ratio then deviates from 1, but fortunately recovers at some other k value further out into k space. And we're going to want to target this second interaction because the density of states is not negligible out there. And so how do we target this state? Well, essentially, we want to choose a photon frequency that is resident with the electron transitions at that particular k value. So in this case, if the AB ratio is 1 right here, we're going to want to target this part of the band structure, which means choosing photons resonant with transitions at this frequency. And since the conduction band and valence band are symmetric, what we really want is 2 times the energy here, which in this case would be 200 millielectron volts. And we can do this for any bias. For example, let's look at 200 millielectron volts. You can see how the shape evolves. And then again for 300 millielectron volts. And at this point, we notice something kind of interesting, which is that the AB ratio appears to be symmetric about the energy bands. It's particularly clear with the black curves. It seems to peak when the energy dispersion is at its lowest. And the reason for this is the simple relationship here. You can show that the AB ratio is simply the bias divided by the energy dispersion. So that's pretty cool. And remembering that we desire the AB ratio to be equal to 1, that implies, according to this relationship, we want to choose a particular k value whose energy is exactly equal to the bias. And if we want to target these energies to induce transitions of these states, we choose a frequency equal to 2 times the energy dispersion, i.e. the band gap, which given this relationship is just 2 times A. So choose a photon frequency which is equal to 2 times the bias. And you should get a strong valley polarization. Well, let's see if that plays out with some numeric calculations. So along the x-axis here, I'm varying the external bias. And on the y-axis here, I'm varying the energy of the center frequency of the Gaussian pulse, of the exciting right-hand circularly polarized pulse. And the color is a measure of the valley polarization, which I plot on a logarithmic scale. Now, the valley polarization is defined by this expression up here, where n sub k is the carrier density at the k point, around the k point, and n sub k prime is the carrier density around the k prime point. So we take the difference and divide it by the sum to get a measure of the valley polarization. And then we plot it on a logarithmic scale to get a better sense of where the valley polarization is strongest. So in particular, if we have, say, a valley polarization of 99%, then 1 minus that gives 0.01. Log base 10 of that is minus 2. And so along this blue curve here, this well-defined blue curve, we have nearly perfect valley polarization. So the way we got this plot was we used a density matrix formalism in which we solved the resulting equations of motion using first-order perturbation theory. So we allow for the linear absorption of a right-hand circularly polarized Gaussian pulse. We then integrate the electron populations around each valley. And then we do that, across a wide range of biases and frequencies, and calculate the Valley polarization that results. Now, for this particular simulation, we fix the number of pulse cycles for all frequencies to be 3.5, but we keep the total number of photons fixed. And so what that ends up doing is meaning that our pulse durations for these trials were on the order of tens to hundreds of femtoseconds. So we have this distinct band of optimal frequency bias pairs where the Valley polarization is nearly perfect. And indeed, it corresponds exactly to where the AB ratio is equal to 1, as we predicted before. Now you can pluck out some optimal parameters from this entire parameter space. They tend to be clustered down here at low biases and low frequencies. And then lastly, this sort of dark red region up here, which seems to be cutting off the overall trend of the AB ratio. Well, that's due to intervalley scattering, which is a process in which electrons at the K point scatter into another valley at the K prime point. And that, of course, destroys our Valley polarization. So that's no good. And here, this yellow curve is basically the onset of that process when the states have enough energy to scatter that way. And so in conclusion, we've derived a condition for strong Valley polarization, namely the AB ratio, and we related that to the energy dispersion and the bias, and that allowed us to derive this relationship for the optimal frequency. We then confirmed that analysis using the numerics, and then from the results, realized that the parameter space is cut off slightly by intervalley scattering. And then finally, the optimal operating parameters you can see here. So thank you.